Hey everyone, welcome back to my channel EduVibe. In today's session, we're moving to the next topic of the atomic physics, which is the mass defect and the kinetic energy. Now we connect the mass defect topic, which is this delta M, with the kinetic energy. How this can be connected, we are going to know in today's lesson. So the mass defect and kinetic energy in the fusion and fusion reactions, they are the times where the energy released via the mass defect may be carried away by the decayed side by a proton, photon, or the gamma ray, which is what we have examined so far. That's all true we examined so far. In these cases, we have ignored the kinetic energies of the nuclei involved in the reaction and any other products of the decay, like beta decay, neutrinos, that all we skip in that case. Other times, we will find that the energy equivalence of the mass defect can be absorbed as increase in system's kinetic energy. Now, when they talk about the energy equivalence with the mass defect, which can be absorbed as kind of the kinetic energy in that case. So the products of the reactions are in motion sometimes. They are not very stable or not very unstable. They are very in motion sometimes, such that your delta EK going to equal to the mass defect C square. This formula originally is that only energy is equal to that, but when they involve in the motion thing in the products or in anything, we'd come to know about the kinetic energy is equal to effect mass C square. We usually assume that the reactants are at rest before the decay, which means that the initial kinetic energy of the system is zero. When we do in the questions, the reactants are in the rest at that case, and before the decay, which means that the initial kinetic energy of the system we taken as a zero. So when we do in some questions, you get to know that how can all the things can be happen in that case. So let's do the questions related to that. Let's take to the questions. The sample of lead 212 undergoes alpha decay. The mass defect of decay is 0.0750 U and is absorbed as an increase in energy of the system. The alpha particle is emitted at the speed of 4.60 10 raised to the 7 meter per second. Determine the minimum wavelength of the gamma photon emitted. Assuming the kinetic energy of nuclei is negligible. So first we have to make the equation of this. So we have a lead which undergoes alpha decay. So this is alpha decay equation. So Pb, which is 212 and have a atomic number of 82, undergo alpha decay, which is 4 and 2. So we have to minus 4, which is 208, and plus 2, which is minus A2, which is 80, which is the Hg, and they mention that the gamma photon is emitted. So we have a gamma thing like this over there, which is released in that case. So that's the equation for the alpha decay, and we have to find the minimum wavelength. To find the wavelength, we need something else. We need some more things, like we need energy first. So we need energy of photon, and energy of photon is can be not like directly can be noticed. So first we start with the kinetic energy, which is equal to defect mass C square, but we don't have a defect mass. So we actually have to find the defect mass now, which is given to us, which is over there. And this has to be in kgs. So defect mass equals 0.0750 U. We have to multiply this by 1.6 in 10 raised to a minus 27 kgs. 1 U and U cancel. So you will get 1.245 into 10 raised to power minus 28 kgs. So you can use this thing and multiply this by C square. You will get a kinetic energy of about 1.1205 into 10 raised to power minus 11 joules. So why are we finding that? Basically, we are going to the step towards to find the thing which we want. So we have a kinetic energy now, and the kinetic energy is negligible, and kinetic energy we take it as 0 in that case. So basically, this thing, that kinetic energy is equal to the final kinetic energy and the initial one. So final at the reactant side, at the product side, and initial at the other side. So EKF minus EKI. So what is EKF? EKF is the final one, final product side, and the product side we have these three things. Kinetic energy of the alpha particle plus the kinetic energy of the Hg. You have to plus this with the energy of the photon. We take that as energy of photon in this minus, and we have a, and the other side we have a kinetic energy of the Pb, which is the light. These things we have, but the mesh energy nuclei is negligible and the reactants are at rest. So your main things, which are the elements in that case, they all go to zero in that case. Always when you do these type of questions, your elements goes to zero, which is Hg in the product side and the Pb in the reactant side goes to zero, and we left with only Ek alpha minus photon, energy of photon. So this thing equal to this plus this. What do we want? For the wavelength, we want the energy of photon. Isolate that thing. This time we isolate, we have this minus, we open this out like this. We find the delta Ek, which is 1.1205 into 10 raised to power minus 11 meters, minus the mass of a particle is given in your formula sheet, which is 6.65 into 10 raised to power minus 27 kgs. The velocity of the alpha particle given to you, this thing. So this has been the square, 4.60 into 10 raised to power 7 meter per second square. And you will get 4.1693 into 10 raised to power minus 12 joules. And you have to put this thing now over there to find the wavelength. So H should be in joules, 6.63 into 10 raised to power minus 34 joules per second, 3.300 into 10 raised to power 8 meter per second. Divide this by the 4.1693 into 10 raised to power minus 12 joules. When you find this, you will get about 4.77 into 10 raised to power minus 14 meters. And this is your wavelength you have to find in that. So that's all thing you have to do, and the main thing in that is this thing. Because this is all the kinetic energy thing, and we have final minus initial we can do with this, and those two zero elements thing, and the defect mass you have to follow to find the delta Ek, which is the defect mass is here. Now when you can add the mass defect to the kinetic energy, then now you have to use that. Then at last we have to use the Planck's constant to find the wavelength. Next question we have, and this is like a question which is the core thing in that, and these are questions you get in your written in your examinations, but you don't have written in your diploma. But then also you have want to be take care of these things, because these are very important things to know. So what you have to do, you have to determine the mass defect of the system and the mass of the uranium-238 nucleus. So you have to find the mass of this and the mass of the mass defect. So uranium-238 undergo alpha decay to produce the thorium-234 nucleus and the alpha particle. So this is actually given to us. Decay of a uranium-238 to thorium-234, the alpha particle forms an isolated system. The main thing, isolated system. When there is isolated system, you all know that this is the talking about conservation of momentum. Where they measure the isolated system, though that means your conservation of momentum you can use in this to find something else which we want. So it means there is a valid conservation of momentum in that case, if there is isolated system. In this system, the energy equivalence of the mass defect is observed as an increase in the system's kinetic energy. Uranium-238 nucleus initially at rest, they mentioned that. Then decays, both the thorium-234 and the alpha particle move away from the location of the decay. They move away from that location. The uranium-238 nucleus has the mass of this 3.89 10 raised to minus 25 kgs. Alpha particle has the momentum of 8.4 10 raised to minus 20 kg dot meter per second. And we have a kinetic energy of 5.3 10 raised to minus 13 joules. So lots of going on over there. What you have to find in this? You have to find only mass defect first. You can isolate the things. Mass defect upon C scale. You don't know the delta EK, but you know the C scale, which is that. So our whole thing to find first the mass defect, to find the delta EK first. Delta EK you can find from the thing we can this in the previous question, that delta EK is equal to the EK final minus EK initial. So what is final, what is initial? So at the final you have plutonium plus the alpha particle, and at the initial you have a uranium which is at rest, so it goes to 0. In that case, thorium is not go away because they not mention it as rest, they mention uranium is at rest. So delta EK, so this is the mass of uranium, velocity of uranium square plus EK alpha, because you have the EK of this alpha particle is if this mentioned over there, so we can't do anything with that. Okay, so what's the things we have in this case now? So delta EK is equal to half. What is the mass of uranium? So mass of uranium given to you over there. This thing 3.89 something. So into 3.89 into 10 raised to minus 25 kgs. But you don't have the velocity for uranium. Now you stop over there and start finding the mass of uranium in that case. So what you have to do? Find over there. So you mentioned that in that case the conservation of momentum is valid, so we can use that thing. Initially we have the momentum for the uranium is equal to the, then in final we have a this thing which is the momentum for the alpha plus momentum for the uranium. This goes to 0 because it's at rest. So momentum of alpha plus the mass of uranium and the velocity of the uranium. In that case, you have the momentum for the alpha mentioned over there. This is that. So you can use that things and find the velocity for the uranium, which is that thing. So to find this, you isolate the things. So this isolate will give you minus photon alpha divided by the mass of uranium. This thing minus, you get 8.4 into 10 raised to power minus 20 kg dot meter per second given to you. Divide this by mass of uranium is given again 3.89 10 raised to power minus 25 kgs. When you get this, so the mass of the uranium you calculate is about minus 2.159 into 10 raised to power 5 meter per second. Why you get it in negative? Because they mentioned that after the decay they go to the opposite directions. But they mentioned that the location, they move from their location. They move from location which is moves opposite direction that the negative sign denotes in that case. Nothing, we can't use the negative sign in that. They just do the direction thing. So now you put this velocity of uranium in this thing, 2.159 into 10 raised to power 5 meter per second. Make sure you use the non-rounded value. Plus we have 5.3 into 10 raised to power minus 13 joules. That is the carry energy for the alpha which is given. And finally you can find the delta EK, which is when you calculate this 5.3906 into 10 raised to power minus 13 joules. Now you get this thing in that defect mass to calculate the defect mass. So 5.3906 into 10 raised to power minus 13 joules. When you calculate this, you get about 5.9896 into 10 raised to power minus 30 kgs in that case. You get your defect mass. But you also want the mass of uranium 238. So let's find that now. So defect mass, you know the mass reactants minus the mass products. So we can do that to find the mass of uranium. So the mass of uranium in the reactant side minus the mass of alpha plus the mass of the uranium at the other side. So we have to find the mass of uranium, which is equal to defect mass plus the mass of the alpha plus the mass of the uranium. Put the things. Defect mass is 5.989 into 10 raised to a minus 30 kgs, plus mass of particle is in your formula sheet, which is that mass of uranium is given to you 3.8910 raised to minus 25 kgs. When you find this, you get mass of uranium of 3.956 into 10 raised to power minus 25 kgs. You get in kgs because all are in kgs. And you get this. So what's the thing you get? So firstly you get the defect mass. You want to round it things. So 6.0 into 10 raised to minus 30 kgs. Two set this. And the mass of uranium 4.0 into 10 raised to power minus 25 kgs. That the two things you can find. So lots are going on. For only the delta EK, you stuck over there. So you could find this over there, delta EK. But to find delta EK, you don't have this velocity of thorium. So actually this is. So you can find this thing over there with this conservation of momentum, which is your physics principle number 4. You can write over there. You can find from here. Then you can go backwards and put the things over there and get your defect mass. Now with the defect mass, you can find the mass of the uranium, which is over there. And you will basically use the things over there conservation of momentum. You use the physics principle number 6 in that case. So 4 and 6, the physics principle is not mentioned, but you know about that. The 6 and 4 physics principle is used in that. And at the end, you can find this both things over there, which is your two things you have to find. So that's how you can manage your work in that case. If the things is not given, use another thing and the other thing and get to the first thing you want. So that's all for this lesson, and we are so far very good in this unit, and we are continue with that unit. There are few copies left with that topic, and yeah, so in that case we start some theory based thing now, not the more calculation thing. So that's all for this lesson. Let me start to EduVibe, learn smart not harder. Please like and subscribe to my channel. If you have any questions, let me know in the comment section. See you in the next lesson. Till let's get it with EduVibe.